Okay, good morning, everyone. My name is Tommaso Macrì. I'm the Executive Grant Manager at QuEra Computing, and I would like to welcome you all to the presentation and the webinar on correlated decoding with logical algorithms with the transversal gates. Today, I'm in a good company of my two colleagues, Harry and Chen. Harry and Chen, would you like to briefly introduce yourselves?
Yeah, hello everyone. I'm Harry. I'm the quantum error correction architecture lead at QuEra Computing, leading some of our efforts on quantum error correction and thinking about how that then translates into implications or designs on the hardware architecture as well.
Hi everyone, I'm Chen. I'm a research scientist working at QuEra Computing, focusing on quantum error correction mostly, on designing new decoders as well as the fault-tolerant architecture.
Thank you, Harry. Thank you, Chen. Before we start with the main presentation, I wanted to briefly introduce QuEra for the people that might not have heard about our company before. So QuEra is a quantum computing company that is located in Boston. We are very close to our academic partners, Harvard and MIT. Our goal is to build and productize quantum computers that are based on a specific technology called neutral atoms that is considered by many to be one of the most promising approaches to quantum computing. Our computer is accessible via AWS since November 2022. And as a very nice announcement, recent announcement, we closed our Series B round led by Google and SoftBank for a total amount of $230 million. We also partner closely with many enterprises, HPCs, and governments to start exploring the benefits of quantum computing. Of course, these different organizations have very different goals to achieve. So, for example, enterprises are interested in position themselves as leaders in this space, and of course, in the specific and how to explore or how to achieve leadership through this dedicated technology. HPC centers typically are a user aggregator, so they have access to many different kind of users, whether academic or industrial users, that want to basically explore this type of technologies and potentially also integrate these new quantum computers with their current HPC systems. In parallel to that, governments may see quantum computers not necessarily as an end, but probably like a tool to basically create new workforce, to attract new talent, research, and boost the local industries and academic efforts. So many countries are now really using or exploring opportunities to partner with quantum computing companies to achieve these much broader goals. How can we help? So one way to see us is as a preference or preferred quantum innovation partner. We try to achieve this goal by both selling quantum systems on-prem or potentially access or providing access to quantum computers through the cloud. Another way that we are exploring with many academic and industrial partners is through collaborative research, mostly on areas that can be dedicated to really leading edge topics such as quantum error correction. We will hear more in the presentation today, but also potentially to understand how hybrid quantum and classical algorithms that can become useful in the short term. We do this with many academic, but also industrial partners. One way to also interact with QuEra is through a new model that we advertised very recently, which is the so-called application co-design. And the main idea of application co-design is really to design and develop applications that make the best use of the current capabilities of quantum computers. The topic that we'll be hearing from Chen and Harry today will be related to one of the major or one of the leading areas of frontier quantum computing, which is quantum error correction. The main idea behind that is that the physical qubits in general are fragile, and qubit errors limit the ability to perform really long and reliable calculations. So one way to overcome this issue is through a field that is called quantum error correction that makes use of one of the central concepts of logical qubits, which are collections of physical qubits that in principle can achieve more performant type of calculations or gates. As a matter of fact, one of the results that we obtained very recently was also considered to be one of the breakthroughs of the year 2024 from one of the major physics journal, which is Physics World. So with this, I would like to pass the word to Chen. Chen, please feel free to share your slides, and we can start with the main presentation. And while Chen is presenting his slides, pulling up his slides, I would like to remind everyone that we have a Q&A that where basically all the attendees can ask questions, and my colleague Harry will be also happy to assist with responding some of your curiosities or questions regarding the presentation. Please, Chen.
Yeah, thank you, Tommaso. Can you see my screen?
Yes, please.
Okay. Hello, everyone. I'm happy to be here to share our recent progress on quantum error correction on this webinar. So this presentation will be based on these two archive papers, and this is a joint work with researchers from Harvard, QuEra, and Yale. And the biggest challenge for scaling the quantum computing up is the error, actually. At the current status, nowadays we have the quantum device that can achieve the physical error rate from 10 to minus 2% to 10 to minus 2 to 10 to minus 3 error rate, while for large-scale quantum computer or for large-scale quantum algorithm that requires 10 to minus 15 logical error rate. And the biggest challenge to fight against those errors and coherence. And fortunately, we have the technique from quantum error correction to bridge this gap, since it will be extremely difficult to suppress the physical error rate directly to 10 to minus 15. And I will briefly introduce what is quantum error correction. Basically, the idea of quantum error correction is that we encode the logical qubit into many redundant physical qubit, and those redundancy will give you the degree of freedom to detect the errors within the system or during the computation. And here, for describe quantum error correction code, we usually use several parameters, where here we use NKD, where N is the number of physical qubits that encode the K logical qubits, and D is the code distance, which is the parameter describe the power of quantum error correction or error correction code. And the most important result in quantum error correction is the threshold theorem, where if the physical error rate is low enough below the threshold, then we can suppress the logical error rate by increasing the code distance D. And this figure demonstrates how the logical error rate can be suppressed by increasing the code distance D, where the slope is the physical error rate ratio between the threshold. The lower the physical error rate, the sharp the slope will be. And the most important example, or the most famous example, is the surface code in quantum error correction, where we encode a logical qubit into 2D grid. And we will utilize the local degree of freedom, which we call the stabilizer, which is defined as the product Pauli operator onto the physical qubit. For example, in the surface code, there are two types of stabilizer. The X stabilizer, which will be used to detect a Z arrow, since the Z arrow will anti-commute with the X stabilizer. And the Z stabilizer will be used to detect X arrows. And by utilizing those local degree of freedom, we can detect the error within the physical qubit, such that those local error will not destroy the logical information. And for example, if there is an X error happen on this physical qubit, then it will anti-commute with the Z stabilizer nearby. And by measuring those Z stabilizer, we can detect this X error, then figure out what error happened during the computation or during the system. And there is another degree of freedom remaining, which is encode the logical information. And for surface code, the logical operator in the surface code will be a string operator connecting one boundary to another boundary. For example, the logical X operator will be the product of string operator connecting from the left boundary to the right boundary in this diagram. And for the Z logical operator, it will be a string operator connecting from the top boundary to the bottom boundary. And all of the logical information will be delocalized. If we want to create a real logical arrow, actually in surface code, we will need to create at least the D arrows, D physical arrows. And D is the code distance. So in surface code, the number of qubits will be d square, where d is the code distance, and the number of logical qubits we encode is 1. So to suppress the logical error rate exponentially, we need only scale up the system size quadratically. And after defining the surface code, that is not the end of the story, since our goal is to perform fault-tolerant quantum computing. And in general, to perform quantum computing fault-tolerantly, we basically need to encode the qubit into logical qubit, for example, using the surface code. Then the other thing we need to do is to convert the logical algorithm, which is defined as quantum circuit, and convert each gate element in the quantum circuit to fault-tolerant gadget, which can be implemented logically. And there are several choices for fault-tolerant gadgets, and in this talk, we will focus on the transversal gate. And the transversal gate is the parallel physical gate which can implement a logical operation defined on quantum error correction code. For example, the logical CNOT can be implemented by applying pairwise physical CNOT, as demonstrated by this animation. Suppose we have several surface code patch, and we move them together, overlapping together, and shine a global laser to apply a pairwise physical CNOT. In that case, if we use the surface code or in general CSS code, we can apply a logical CNOT with only applying the physical CNOT. And this is very efficient on neutral atom platform, since we only need constant complexity to control the logical qubit, since we can move the qubit in parallel and shine the global laser to apply the gate in parallel. While the transversal gate requires higher dimensional connectivity, which is quite challenging for other platforms other than the neutral atom platform, but it is natural for neutral atoms. And there are some challenges from the transversal gates, since the error mechanism is quite different from the other logical gate or logical fault-tolerant gadget. And the most important property in transversal gate is that the error will not spread within the code block, or the error, since we only apply local operation within the code block, but the error can spread between the code block. For example, when we apply transversal CNOT gate between two surface code patch, the X arrow, physical arrow, on the control qubit will propagate to the target qubit, and the Z arrow from the target qubit will copy to the control qubit. That means that the physical error on one single logical qubit contains the information about which error occurred on the other logical qubit. And intuitively, if we can utilize this information during decoding, then the performance of decoding or the accuracy of the decoding can be higher. And this research is actually inspired by the experiment led by Harvard, where they prepared two logical qubits into plus state and zero state, and apply a transversal signal between those two logical qubits to prepare a Bell state, which is a superposition of 0, 0, and 1, 1 states. And after measuring XX operator or ZZ operator, which is the stabilizer of the Bell state, we can detect whether there's an error happen within the Bell state preparation. And interestingly, we found that if we applied, if we consider the correlation between the error within the transversal gate, then we can suppress the error by increasing the code distance exponentially. However, if we ignore this correlation, then if we increase the code distance at the current physical error rate, the logical error rate will actually increase. And this is the first demonstration of the entangling operator that can be improved by increasing the code distance. Let me think about this phenomenon in detail, more theoretically. Suppose we are doing the same experiment by preparing a plus state and zero state logically, and then suppose all of the error happen are X error or Z error before the transversal C naught, and after on the other place of the circuit there's no error, we suppose, and intuitively the error will copied. If all of the error happen before the C naught, then after the C naught, the error will be copied. And during the measurement, we can detect those errors, but the error density will effectively be doubled on each logical qubit. And if we don't consider the correlation between those errors between logical qubits, then if we decode each logical qubit independently, then the threshold will be halved because of the error density doubled. And by comparing the threshold, where the threshold is the physical error rate, below which the logical error rate can decrease exponentially by increasing the system size. And here in this, this is the numerical simulation result. And in this diagram, different lines represent different code distance, and the lighter means the lower the code distance. And before some point at the physical error rate, you can see that the code distance, when we increase the code distance from low to high, then the logical error rate can be suppressed exponentially in the log-log diagram. And we compare the performance by comparing the thresholds of the uncorrelated decoder and the correlated decoder. What we observe is actually what we expected, where the thresholds is almost nearly halved. And as a result, the correlated decoding can improve the threshold, which means that it can improve the performance of quantum error correction. However, during the computation, we usually need to detect the error using the process, what we call the syndrome extraction. And in practice, the syndrome extraction is also implemented using the noisy surface, noisy physical operator. So the syndrome extraction process itself is noisy. And for example, when we measure the X stabilizer within the surface code, we will introduce an ancillary qubit and entangle this ancillary qubit within the data qubit that encode the logical information. And after entangling, we will measure the ancillary qubit. And if there's an error happen on the ancillary qubit, this error cannot be this error will flip this syndrome extraction result or the stabilizer measurement result. And in practice, we will repeat the number of rounds of syndrome extraction to make sure we gain enough fidelity or gain enough confidence about those syndrome extraction results to detect the error within the data qubit correctly. And as a result, conventionally, when people think about constructing a logical gadget or a logical fault-tolerant gadget, we will usually, after applying the logical operation corresponding to the logical operator, we will actually apply d rounds of syndrome extraction to make sure the fault tolerance of this logical operation, and it will introduce additional time overheads from the noisy syndrome extraction. In practice, it will reduce the logical clock speed d times slower than the physical clock speed. And for a large-scale quantum algorithm, for example, the factoring algorithm or quantum simulation algorithm for material science or chemistry, the distance requires for those large-scale algorithm will be around 30. Which means that the logical clock speed will be at least 30 times slower than the physical clock speed. And a natural question is that can we optimize this time overhead? And when we consider a simple example where we create a stabilizer state using the transversal Clifford circuit, where we prepare several logical qubits into plus state and apply random Clifford circuit to prepare stabilizer state. And at the end of the circuit, we will measure all of the qubits. And after each layer of transversal entangling gate, we will insert the stabilizer measurement or syndrome extraction. And the issue we need to, why we need to insert multi-round or d-round of syndrome extraction is that the syndrome extraction measurement result is noisy, and we need to verify by repeated its d-round. But fortunately, if we apply all of the logical operator using transversal gate, then the error propagation is deterministic. Then actually we don't need d-round, since if suppose there is an X stabilizer measured here, and this stabilizer will be propagate to two Z stabilizer across two different logical qubits. If we want to verify if this X measurement result is correct, then we can just take the product of these three stabilizer measurement results and to see if the parity is the same. Which means that the syndrome measurement on different transversal logical operation can help each other to verify each other. And the cost we need to pay is that we need a correlated decoding, since the syndrome measurement will be propagated into different logical qubits. Then in that case, we need to usually decode the logical circuit as a whole instead of decoding each independent logical qubit. And by conducting the numerical simulation by using different correlated decoder, one is a polynomial time belief hypergraph union find decoder, the other is the suboptimal exponential time most likely error decoder. What we found is that there's a clear threshold observed for each decoder, each correlated decoder, which means that if we apply transversal gates and correlated decoding, then the fault tolerance of the arbitrary Clifford circuit can be preserved with only order 1 time overhead, which means that we only need constant round of syndrome extraction within the circuit after each operator. And a natural question is that how can we generalize this result to universal quantum computing? Fortunately, the only missing part for universal quantum computing is the non-Clifford gate, or the magic gate. And the magic gate can be implemented using magic state and teleported into magic gate using feed-forward Clifford circuit or adaptive Clifford circuit. And if we assume low noise magic state input, and if we can implement the adaptive transversal Clifford circuit fault-tolerantly, then we can implement the universal quantum computing fault-tolerantly. For example, if we want to apply a T-gate, we can use the protocol which is called the T-teleportation, which means that we will prepare some T logical states and entangle with the qubit we want to apply T-gate, and then measure this ancilla resource state. And based on the measurement result, logically, we will apply a transversal or S-gate on the qubit we want to apply T-gate. And that means that if we interpret the measurement results on this Z measurement incorrectly, that may lead to incorrect feed forward. And it seems like to be a major problem for this generalization. And the key question for this generalization is that, can we always interpret the new measurement result correctly? Otherwise, we will make mistake on the feed forward. The major challenge here is that we don't have enough information on the remaining qubit. Since we only measure this qubit, we do have enough confidence on the stabilizer on this qubit, but not on the remaining qubit. And on the remaining qubit, there are usually some uncertainty from the initial stabilizer, where we initialize the plus state. For example, here, when we initialize the plus state, there are some non-deterministic stabilizer. All of the Z stabilizer are actually non-deterministic. And if we don't have enough confidence on this stabilizer, then those initialization error might create some logical error. And what we observe is that the initialization error actually propagates like the logical stabilizer. For example, the logical stabilizer for the plus state here is the X stabilizer. And this X stabilizer will actually flip this measurement result. And we analyzed this situation in detail to see whether if it is an issue or not. And the only thing we need to consider is the logical stabilizer. And if all of the measurement we rely on feed forward, the measurement commutes with all of the logical stabilizer, which means that the measurement is not sensitive to the initialization error. And by applying correlated decoding intuitively, the measurement result will be correct if we consider the correlation between the different qubits. And what we prove is that we prove a threshold theorem that's applied to when we apply correlated decoding, that we can suppress the logical error rate, in this case, exponentially by increasing the code distance if the measurement, if the logical measurement commute with all of the logical stabilizer. However, there's another case where the logical measurement anti-commute with one or more logical stabilizer. And in this case, the logical measurement will be 50-50 random, which means that the measurement is sensitive to the initialization error, and we must be consistent with the prior measurement, since we already applied the feed-forward operation based on those measurement results. For example, if we at the first round of decoding, we decode these two logical measurement results and apply feed-forwards based on these two logical measurement results. And at the second step, when we have further operation and further logical measurements, we need to decode this circuit again, because there are some updates from the remaining qubits compared to the first round. The belief on the initialization error might change at the second step decoding. Then in that case, the decoding result on this previous logical measurement could change when we apply correlated decoding. But fortunately, we can directly apply those logical stabilizer to flip this measurement results back, which is consistent with the previous decoding result. And in that case, we prove that the application of the logical stabilizer doesn't change the measurement distribution, but only change the way you interpret those measurement results. In that case, we can guarantee the consistency between different rounds of decoding. And the theoretical result we prove is threshold theorem. Using this process by applying transversal gate on QLDPC code and apply correlated decoding and considering the logical stabilizer flipping to guarantee the consistency between different decoding rounds. Then we can suppress the logical error rate by increase the code distance. And we verify this theoretical result by numerical simulation, and we compare our strategy with another fault-tolerant gadget strategy named lattice surgery, where in lattice surgery, we can achieve logical operation in 2D in only 2D connectivity. However, it will require D round of syndrome extraction if we don't. And here we consider if we only apply single round of syndrome extraction or constant round of syndrome extraction using both transversal gate and lattice surgery. As we proved in the transversal gate, the logical error rate can be suppressed by increased the code distance exponentially. However, for lattice surgery, it doesn't work since each lattice surgery operator will introduce some new stabilizer where we need D round of syndrome extraction to gain enough confidence on those new stabilizers. And another example we conduct the numerical simulation is the state distillation factory, where those state distillation factory will be used to prepare high fidelity non-Clifford state or the T state in practice. And the idea of the state distillation factory is that we will input some noisy resource state, and by detecting the errors within the noisy resource state by quantum error correction code, we can output a distilled resource state with higher fidelity. And here we consider the white state distillation, which has the very similar structure as the commonly used magic state distillation for the T state. And the white state distillation is actually simulatable, but with the similar structure, we expect the same result will apply to the T state factory. And we inject different input state with different fidelity and see if the error correction can suppress the logical error from the to match the output fidelity theoretically. And what we observe from the single level distillation and two level distillation, if we increase the code distance, then the output fidelity from the distillation factory will converge to the theoretical optimum. And in conclusion, we will call this fault-tolerant strategy the transversal algorithmic fault tolerance, where in the conventional fault tolerance we need D rounds syndrome extraction per operation, but we can decode each single operation independently or decode a single logical qubit independently. But for our case, when we consider the transversal gates, actually we don't need D rounds. We only need constant round syndrome extraction per logical operation. But the cost we need to pay is that we need to decode the whole algorithm correlatedly. And the three important ingredients for the transversal algorithmic fault tolerance is the transversal logical gate plus the correlated decoding and the other strategy or other technique we introduced to handling the feed-forward to guarantee the consistency for a non-Clifford gate. And all of the technique will give us a factor of D speed up in practice, which can reduce the computation time from several months or a year to only several days. And all of the results are supported by theoretical proof and numerics. And for future works, we want to consider to combine this fault-tolerant strategy to low space overhead scheme. For example, the recent progress on the QLDPC code. And also we want to consider the hardware architecture design for neutral atom system to actually run this theoretical result in practice. And in practice, we will need a faster decoder, which will give us a real-time decoding result such that we can apply the real-time feed-forward. And this is collaboration work with a lot of researchers from Harvard, QuEra, as well as Yale and AWS. And I want to thank all of my collaborators. If you are interested in more details, you can scan this QR code for the detailed paper. And thank you for your attention.
Thank you so much, Chen. Thank you for the very nice presentation. I would also like to thank Harry for the several answers that he gave to the questions that we received on the Q&A. I wanted to also ask, perhaps, Harry, if you are online.
Yes.
Just to put a little bit more in the bigger picture or bigger perspective, the work that Chen presented. How close are we to a more realistic implementation of these techniques? Of course, in the context of our neutral atom quantum computers.
Yeah, that's a great question, Tommaso. In many ways, many of the basic ingredients have actually already been demonstrated both in the previous pioneering Harvard 48 logical qubit work, where these transversal gates were performed. And in fact, that was indeed the original motivation for looking more carefully at the fault tolerance and trying to understand, okay, do the savings that we see there actually really apply quite a bit more generally than originally was done in those experiments. But I think also going forward, this will be an important tool in our toolkit to be able to utilize these native capabilities of neutral atom systems to accelerate computation and make error correction a lot easier for our platform.
Oh, that's excellent. Thank you, Harry. I would like to thank Chen again. Of course, feel free to reach out if you have any additional questions or curiosities. We have seen a lot of movement during the presentation by Chen. And to conclude the webinar today, I would like to already advertise the next episode of our QuEra webinars, again with Harry, as well as with Pablo, who is a PhD currently at Harvard, on constant overhead fault-tolerant quantum computation with preconfigurable atom arrays. So with this, I would like to thank you all again, thank our presenter, Chen and Harry, and we'll see you soon then on May 27th. Thank you so much.